Hey everyone. So today we'll be discussing about the data and data engineering, and we'll be entering into the field of data engineering. So before that, let's first talk about the data. Okay, so we'll be talking about the data, and I'm your host, DataSpark. We'll be talking, and the first time in English the use of word data was utilized in 1640, that is in, and next the usage was in the 1946, which was actually in the context of the storable computer information. Soon the word data processing came into picture, which was actually around 1954. Okay, but the etymology and terminology of the data was before the development of computing devices and machines, people had to manually collect the data and impose pattern on it. Ever since computing devices and machines came into an existence, these devices can also collect the data. So analog computers and represent the data as the voltage, distance, position, and these kind of physical quantities was something it used to collect. Now digital computer is a piece of data that is a sequence of symbols and using the binary numbers like denoted as zeros and ones, and this was how the data was collected. Hence computer program is a collection of data which can be interpreted as an instructions. Okay, but first, the unstructured programming language. How did all of this start? Of all of this, the programming language at all first came into an existence was the BASIC and FORTRAN. These were the unstructured programming style. It was very difficult to understand because you see the screen on the towards the blue color, this side, this is the actual code which was written in BASIC. Okay, and as you can see, it was so difficult and more complex problems we could not like be able to solve. Only simple calculation of some circumcenter or area perimeter or this kind of smaller things can be calculated, and there were actually no coding standards. The controls used to go up and down. There is no specific execution or a way to actually write it. Then after some sort of improvement, then came modular programming style, where some of the examples of modular programming style is COBOL and PROLOG. These kind of things, what actually happen is breaking a bigger problem into a smaller problem. So let's say that if there is a sort of a big problem that is there, that has been broken down into smaller bits of pieces and been assigned to a different team so that they can solve each particular tasks, and they could combine together to solve a bigger problem. But the issue with this is the output of one particular team was an input to another team. So all the teams that had dependent on particular team had to wait in queue so that they would get as an input. So because of which they could not scale in a larger problems when they enforced. And one quick thing to know, one small important thing to know is PROLOG is declarative programming. You can declare and you can have some sort of function to write it. You can see here there is a function called inspect function reverse, which takes a string parameter and then reverses something like that. So this is just an example. Okay, and some of the the limitations is one phase gets delayed, then the other work gets halted. So the other teams have to wait for the new team or the previous team to give an input. And even for a smaller requirement, they had to code a huge large lines of coding. So this becomes a very difficult when there is a knowledge transfer. When a new resource comes into the team, they had to deliver the knowledge to them. Then came our structured programming language, that is C and PASCAL. So this is a we had a separate function for each of these functionalities, and the limitations was the performance issue. It takes too long for even a small phase, and considering that if you have something, if you see that the C language do not have the classes. So let's say that in a telecommunication example, let's say that we have Virgin Mobiles or Airtel or AT&T. That particular SIM, that particular company has too many customers, and if we have to find the particular account details, let's say that we have to find account balance, okay, for that particular customer, okay, that particular customer. It was difficult to find among all the customers which they had, because it is a linear fashion execution, does not have the functionality to get by using classes. We cannot invoke those things. So these kind of things, when there was huge data, it was very difficult for them to fetch, and it took a lot of time to find it. And since it is not object oriented, obviously there is no class and object concept, and this kind of programming take huge memory allocation from the operating system as well as the system on which it was running. Hence, to solve all of these problems, we actually came into an object oriented programming language, which is why the object oriented programming, the whole the concept of polymorphism, inheritance, constructors, all these things came into a picture. Threads, multi-threading, everything came into a picture because of object oriented programming language. And this was revolutionized, because of which they actually started having applications, building up larger applications, building web applications. It was possible only because of object oriented programming language. And let's deep dive into it, what actually happened. The history of actually large scale distributed computing system, actually, because the developer started building in applications. So we created software applications and deployed them on computers. These applications needed to do a lot of things, including processing, and it's not limited to only storing and processing the data. And over a period of time, the data kept growing, hence the requirement of the storage and computation power was increasing. However, this was fulfilled by rapid advancement of storage and computer hardware. Our applications started storing more and more data and kept becoming faster and faster by simply upgrading the hardware. Just like you can see it on screen, the system which was the above one is very old, and now we have sophisticated systems. However, the advent and rapid adoption of the internet disrupted this perfect harmony. The scope and the reach of the software applications started to expand across the geographic boundaries and covered entire planet. As a result, the data began growing and evolving exponentially. It wasn't possible and practical for hardware technologies to catch up with the growing and disruption, but we needed a solution. So how exactly did this happen? How did the evolution of this kind of take place so drastically? We'll talk about it. Now, you see on screen, all these are object oriented programs: C++, Java, C#, Delphi, Ruby, PHP, Emerald, Scala, Oberon, Perl, and many more. There are Lisp, Groovy, Android, iOS. See, there are many object oriented programming languages. So if using this, they have JavaScript, all these things. They started building standalone applications and web applications, and they started storing in Excel, or maybe comma separated value, that is CSV, and TSV, that is stat separated value, and maybe all these things you can consider as flat files. There was an era more applications were able to build, so which is why all these things they were using to store. The normal flat file could not manage, and web applications needed a database to store the data for quick validation and authentication. Data was then stored in the databases. Since it was efficient during that time, it became a boom, and more database developers were needed to manage the data. Soon, people started to realize the importance of the data they were able to capture of the customers. They could use it to get more sales and revenue and grow company, but the data was so huge to analyze. So that is the reason they started having larger database with large storage unit, having their replications mirroring those data into different servers. And they needed proprietary tool to perform data warehousing. Hence came data analytics and ETL softwares like Informatica, SSIS, Pentaho, this is Pentaho, Talent, ClickView, all these things came into picture when they started storing it into a data warehouse. And from the data warehouse, they started connecting Pro Workflow, Power BI, Tableau, MicroStrategy, and many more reporting tools to develop beautiful dashboards and data visualization dashboards and reports to their business holders, stakeholders, VPs, AVPs, CFO, CMO, CEO, for everybody. Now, but this whole thing which you see, this sort of setup is called monolithic. Okay, this is called monolithic, but we'll discuss what exactly it means monolithic in the next few slides. But this whole structure of using proprietary tool to do this kind of analytics was considered to be a traditional system, or you can say it as a monolithic. With large servers, this means there's only single server which can manage, although there are replication factors like replica of the servers, but still this was monolithic. Fast forward to the data collection became so huge that even large storage servers and warehouses began giving up the scalability. Okay, and how much data are we talking about? The important stats which you need to know is there are so many messages that has been generated by WhatsApp users per minute. I'm not sure this number, even 41 million, I guess it's around 4. Yeah, it's 41 million, and then it's around 1.3 million video calls have been done by various sources of social media. I mean, be it Instagram or maybe WhatsApp, FaceTime, or any other proprietary tool which you had used, and around 400k hours of video has been streamed by the Netflix users per minute, and around 350k stories have been posted on Instagram users per minute. And all of this data is as of 2020. I did not collect for the 2021 or 2022, but these are around 2020, and you can always expect this data could be more even now, because the users have been constantly increasing in these tools or applications. Now, coming to the fact, in 2024 it is expected to be around the world, the data would be generated around 149 zettabytes. This is an approximate number, but still this is a prediction that all the data engineers from a top companies have been predicting that in 2024 there will be around 149 zettabytes. It could be more, but yeah, this is what it is. But if you consider 2021, it's around 74, but if you see 2024, in just 3 years it almost doubled in zettabyte. And considering, if you see just the double value, it's not the point. It's the point is it is the zettabyte. It's not in few GB or petabytes or something like that. It's a huge volume. And if you ask me as a data engineer, like how much data has actually been utilized, I would say not even 10% of this data have been analyzed and captured and stored. Now, the big question, what is big data actually then? If you consider, okay, all these are fine, but is this big data? I mean, would you call large variety of data? We saw video call is a kind of a data, message is a different types of data, it's a text data, it's a video data, it's a audio data. Do you call variety of data, or some say volume? Do you call big data based on volume? If you have larger volume, it's a big data. Or is it some say that larger data set, the set of the data becomes huge, then it's a big data? Then we'll discuss actually how it is been coined as a big data. We have 8 B's on which we can consider as big data. We have volume, we have velocity, we have variety, we have viability and value, veracity, validity, and volatility. These are the 8 important V's that needs to be considered if we have to call some sort of data as the big data. But do we really have to consider all of these 8 V's to call as big data? Well, need not necessary. We have 3 V's that is very, very important. That is volume, variety, and velocity. Some of the volume, like different kinds of volume of data, insurance transactions, stable files, sensor data, traffic signals data, if you have doing IoT, those kind of devices data, scanners data, all these health records, or FMCG data, all these things comes into volume. And varieties are structured, unstructured, semi-structured, What is structured? The tabular format. What is unstructured data? Raw files like audio files, video files, like semi-structured, something like JSON, all these things, semi-structured data. And what type of processing that they do? Though batch processing, in a batch, near real time, near time processing, real time processing. That means as soon as the data arises, it needs to be processed. Near time is like, there is a lag of 5 minutes, 10 minutes, 1 hour difference. Streaming data, as soon as the data has been found or captured, immediately processing through when it is coming through the platform or proprietary tool. So these three are minimum. These are the three V's of the big data. This minimum, these three V's need to be there in order for us to call a particular data as a big data. The formal definition provided by IBM that any data that can be characterized by three V's is considered to be as a big data. But apparently now IBM has updated that. We call it as 5 V's, but you can see those things in the link that I have provided in this slides. Okay, now, okay, theory is nice, but why actually big data? Why do we need to have the big data? First, to be honest, we need to store those data, that's huge data, and then we need to process it. So there are two things. We need to store the data and we need to process it. So first we need to store the data and then we need to process. Okay, but the traditional systems are not suitable, fit to store such huge amount of data and process it. You saw those proprietary tools, it cannot handle large data, and with the growing data in this like in this generation, in this speed, they will not be able to cope up in future. At one point they will give up. Right now there are some still projects that are still running on monolithic traditional system, but eventually they will give up. Now, what are the ways in which you can build the system? There are actually two ways. There are two ways to build a system, and that is monolithic and one is distributed. What is monolithic? Now here we came to a picture where we had stopped in our previous slides. We told that we said that it's monolithic. What actually is monolithic? Monolithic means there is only one powerful system with lot of resources. But what is distributed? Many smaller systems come in together to become one small cluster, and in that an individual system is coined as node. Okay, that is considered as a distributed system. But we should also know the fact that just because we provided a solution, we should also see that whether it has a scalability. Now, what is a scalability? See, today in your project, they are getting around 5 million records. To process that 5 million records, you are solving some sort of server. You have a particular server and you have particular tool which is able to solve it. Now, you in future, 1 year, 2 year down the line, that 5 million record becomes 10 million or 15 million. Does your project, does your tool, does your server is able to manage the load? This is called scalability. Scalability means as and when data grows, your requirement also increases. The system should automatically increase, grow and scale along with the requirement, and as and when the data grows. This is called scalability. Does monolithic system has this kind of scalability? Definitely no. It's a proprietary tool. They have their limitations. A 1 GB server, 1 GB database, if you consider an example, it can store only 1 GB. You can increase that, but what about the performance? We'll talk about that. Now, let's say a question for you. Have you ever seen a 1 petabyte of RAM system? Ever? A laptop or any system that has such a huge RAM? Or have you seen 1 TB or 1 exabyte RAM? No. Maybe it can be there, it might not be there. No, it may not be there. We'll soon know why we do not see such a huge RAM. Because obviously we have a system with our personal laptop, or a system which has maybe 8 GB RAM or 16 GB RAM, those kind of RAM with some processing unit, that is CPU. We have RAM, that is memory. We have a storage, that is hard disk. which you call as HDD, right? So these things are necessity in order for a laptop or a system to run, a computer to run. But do you see that 1 petabyte of RAM system? No, I don't think so. Commonly you don't see that, but why? We'll see that soon. Now, is monolithic scalable? We had this question before. Definitely it's a no. Why? 2x resources becomes 2x performance? No, monolithic does not scale like this. Okay, it doesn't scale. Let's say that while you are doubling the resources, your performance is doubling up. Okay, assume that you have a laptop which has 8 GB RAM, okay, and 1 terabyte of hard disk. At one point, when you need more speed, when you double the resources, 16 GB RAM and 2 terabytes of data, it increased the performance, it doubled. Means any job which you were doing, let's say that it was taking 2 hours, it is now taking 1 hour. Cool, very good, fantastic. Now the data started growing again. Now you thought again it is taking 2 hours with 16 GB RAM and 2 terabytes of hard disk. Now you think I will make this RAM 32 GB RAM with 4 GB storage, and when you ran that particular task, it did not make 2 hours to 1 hour, rather it completed in 1 hour 15 minutes or 1 hour 45 minutes or 1 hour 30 minutes. Why? It should have been 1 hour, right? No. In monolithic system, 2x resources does not mean 2x performance, meaning some of the resources is getting wasted. This is why we say monolithic cannot scale after a certain point, and this is exactly the reason why you do not see systems with 1 terabytes of RAM. Got it? Now, okay, everything's cool, but what is distributed computing system? What is distributed system then? Now distributed system means it is collected with many smaller systems. Consider 8 node cluster. This is 8 node. Remember what is a node? It's a small machine. Individual machines is called node. So this is a machine, this is a machine, this is a machine. All these are nodes. We have 8 nodes that are connected together. This whole thing is called 8 node cluster. Okay, can we double the performance? Let's say that in this cluster, let's say a particular job, a particular task is completing in 2 hours. Can we double the performance? Yes, it's very easy. Just add 8 more machines to this cluster, the performance gets doubled. That means the task takes 1 hour. If you add 16 more machines, it starts to take in 30 minutes. This means 2x performance you will get by increasing the resources 2x. That is, this is called distributed system, and adding machines is called distributed system, not increasing the RAM. Got it? But if you still have any confusion, I'm sure that in next further slides you will get clarified. Now actually how it looks like, the monolithic architecture and the distributed architecture. Monolithic architecture means it is vertical scaling, and distributed architecture means it is horizontal scaling. People usually get confused what is vertical scaling and what is horizontal scaling. Monolithic architecture is a vertical scaling. That means adding only one particular system but increasing the resources within it. 2 GB RAM to 4 GB, 4 GB RAM to 8 GB, 8 GB to 16 GB RAM, 16 to 32, and so on. This is vertical scaling, and also goes with the storage as well. 512 GB storage to 1024, that is 1 terabyte, 2 terabytes, 4 terabytes, 8 terabytes. No, this is called vertical scaling. Distributed is adding more machines. Okay, now we'll get more clarified if you see this particular image. I see the vertical scaling is increasing the size of instances, that is RAM, as you can see, and horizontal scaling looks like this, adding more instances. Okay, now the first person to realize this issue This problem is none other than Google. Google was not only the first to realize the problem, but also the first to develop, or to create a viable solution and establish a commercially successful business around it. They were creating a search engine. The first thing they wanted to do is to discover and crawl the web pages over the internet and capture the content and metadata. These type of problems are now characterized as data collection and data ingestion problems. Once the data is collected, they wanted to store and manage it. However, they are going to collect this massive amount of data on a planet scale. So the next problem was to store and manage hundreds of petabytes of data. The next problem they got was the computation power for processing those massive volume. They wanted to apply something called page rank algorithm on the received data and create an index. So the third problem was to also require processing power. And finally, the last problem was to organize and store this kind of outcome into processing. So in Google's case, the result was index. So they were facing issue with this. They wanted to keep it in random access database, and they can support high speed queries for Google search engine the application. So Google successfully solved these problems, but they did not actually implement it, but they actually provided a theoretical solution, and those two solutions are in these two research papers which are shown on screen. That is, in 2003 and in 2004 they developed a white paper called Google File System, which released in 2003, and MapReduce white paper on 2004. Great, fantastic, beautiful to understand. But here comes actually architecture. In 2003 they gave Google File System, that is this research paper, and in 2004 they developed MapReduce. They gave this paper. Yahoo took these papers and gave, sorry for the typo here, it's actually papers, and gave a software implementation to these papers. They took this, hey, you know what, let's collect these people, let's see what they are up to, and they took these papers and they actually implemented it, and they renamed the Google File System GFS to HDFS, Hadoop Distributed File System, and MapReduce was the name. They kept it unchanged. And in 2009 Hadoop came under Apache Software Foundation and it became open source. Okay, beautiful. And thus the Hadoop was born. So it was actually developed by Yahoo, but during that time there was something, they were building some search engine or maybe an application called Nutch, and there was some engineers who were working on it. It was search engine of Yahoo. It was open source software, the search engine. So at the same time Google also published this white papers, and they were like, Yahoo were like, why not, let's give it a try. So at that time on which the white papers published by Google, it was Doug Cutting and Tom White. They were working on that particular project. In 2006 they finally came up the name called Hadoop, and the story goes by that Doug Cutting's son had this cute little elephant, yellow elephant, and his the toy name was Hadoop, and they named this particular technology as Hadoop. But wait, we'll not process this any further, will not proceed this further, because once we start Hadoop, that's a huge ocean. We have already stepped into the data engineering. If we are supposed to talk Hadoop, it's a huge topic, and if I start this, I won't be able to finish this. Definitely I won't be able to finish this in not even 1 day, 2 days. It'll take many days. So it's a big ocean, and I don't want to spend more time on it, because let's take that into another session. But I hope I have stopped this session an extremely very beautiful curious point. But if you're really interested, if you are staying with me, please wait for the next session. I'll release this video maybe about Hadoop from basic, and I hope I'll make it as interesting as possible. But I really thank you for staying by, and I hope you like this session. Stay tuned, stay safe.